Mr. You are in a heap of trouble, Mr. Julian Kiabu. I'm very disappointed that you have failed this physics test. You should have studied better. And I'm gonna have to see you in tutorial today.
Yes, Mr. Louis.
Do you feel disappointed in yourself?
Yes, Mr. Louis.
That's more like it.
Yes, Mr. Louis.
What is up, guys? Vince here. Today I'm going to teach you about Boyle's law and Charles' law. Mainly, this section will cover pressure, ideal gases, the pressure volume law, Boyle's law, the volume temperature law, Charles' law, the pressure temperature law, Amundsen's law or Gay-Lussac's law, and the equation of state of an ideal gas. So stay tuned and I'll explain everything here in this classroom. Alright, I'm going to summarize all three laws, Boyle's law, Charles' law, and Amundsen's law, in under 3 minutes using a rap. So there's going to be 2 raps, and one's going to go for Boyle's and Charles', the other one's going to go for Amundsen's and the state of an ideal gas. So let's get it.
Pressure is defined as a normal force applied per unit area. The unit of pressure is Newton per Newton. Pressure is defined as a normal force applied per unit area. The unit of pressure is Newton per square meter, also known as Pascal. Another commonly used non-SI unit is the atmosphere. An ideal gas is a theoretical model of a gas. It helps us to understand the behavior of real actual gases. We assume that an ideal gas obeys the following. Molecules are point-point particles. Molecules obey the law of mechanics. No forces between molecules except when molecules collide. Duration of a collision is negligible compared to the time between collisions. Collisions of the molecules with each other and with the container walls are elastic. Molecules have a range of speeds and move randomly. A real gas may be approximated by an ideal gas when the density is low. In Boyle's law, at a constant temperature and with a fixed quantity of gas, pressure is inversely proportional to volume.
3, 2, 1, go!
Temperature is expressed. Alright, let's move on to Charles' law. When the temperature is expressed in Kelvin, this experiment is at constant pressure, which in turn the equation is V over T equals constant. For Gay-Lussac's law, or Amundsen's law, when the temperature is expressed in Kelvin, this experiment implies that it's at constant volume, which is P over T equals constant. In the state of an ideal gas, the equation is PV equals RNT. Remember that temperature must always be in Kelvin.
3, 2, 1, go!
Alright, now let's review all 3 laws including the equation of state of an ideal gas. Boyle's law states that. Alright, now let's review all 3 laws including the equation of state of an ideal gas. Boyle's law states that. Alright, now let's review all 3 laws including the equation of state of an ideal gas. Boyle's law states that the pressure and volume of the gas have an inverse relationship when temperature is held constant. In Charles' law, when the pressure on a sample of a dry gas is held constant, the Kelvin temperature and the volume will be directly related. In Amundsen's law, it's the relationship between the pressure and the temperature of a gas. In the equation of state of an ideal gas, the Boyle's law states that at constant pressure is inversely proportional to volume. And for ideal gas, the equation of P states PV equals to nRT.
Alright guys, thank you for watching. I hope you guys had as much fun as I did making this video. But if you have any other questions or things that you don't understand, please refer to the study guide that I made. So the study guide is more of an in-depth review of all the laws that I talked about, even the state of an ideal gas. All the equations and the definitions are in there, so it's more specific, since this video was primarily about the rapping part. And if you enjoyed, like and subscribe. See ya! Alright, next up we have Juicy J's video. Check it out.
What up, Physics Nation? It's your boy, Physics Man, and today we're going to talk about Ludwig Boltzmann, an Austrian scientist and philosopher, and his contributions to physics. Let's get into it. So first, let's talk about the kinetic molecular theory of temperature, one of Boltzmann's major contributions to the physics world. He theorized that within a container, particles are constantly moving, all at random speeds, having elastic collisions. Not inelastic, I was wrong, okay? Elastic. And he theorized that when these particles come into contact with you, their kinetic energy gets converted to heat energy through energy transfer. So therefore, high velocity equals high temperature, low velocity equals low temperature. Density is important in this equation, as I just erased, because the more particles there are in a container, the more collisions can occur. Next, we're going to talk about kinetic energy. Kinetic energy, the derivative of kinetic energy, which is Boltzmann's equation of Ek is equal to 3 over 2 Boltzmann's constant times temperature. This is important because it relates velocity of the particles in a system to the temperature in Kelvin, not Celsius. Wikipedia made it clear that it was not in Celsius. So, moving forward, there are 3 equations that are used to get this equation. The kinetic energy equation, 1 over 2 mass times velocity squared, the pressure equation, 1 over 3 density times c squared, and the ideal gas equation. C is very important, as I keep writing, because that specifically deals with the speed of these molecules. So, if we start off with the kinetic energy equation and we take V, to find the average of V, we take all the velocities of the particles and we divide them by the number of particles. We know that C is defined by the RMS speed, which is the root mean squared speed. So, in order to get that from the average velocity of these particles, we say C is equal to the speed of these particles squared over the number of particles square rooted. So, with all that in mind, we can say that Ek is equal to 1/2 mass times c squared. Next, we take our big old physics equation machine and we throw in our 3 equations. That's in and outside. Kinetic energy, pressure, and ideal gas, while keeping C in mind. We throw all these in, and then out we get Boltzmann's equation with his constant Ek. The average kinetic energy of all these particles is equal to 3 over 2 Boltzmann's constant times time, or temperature. Temperature, not time. To learn more about these, you can tune into our next video. Thank you.
Okay, now let's take a look at Sierra's video.
Before we learn about Avogadro's number, you should be familiar with what a mole is. A mole is a chemical mass unit that is defined as a mass of substance containing the same number of units of carbon-12. Units may be atoms, molecules, formula units, electrons, protons, or anything. Avogadro's number is 6.02 times 10 to the 23rd power. 1 mole is equivalent to that, therefore it became known as Avogadro's number, named after this handsome Italian scientist Amedeo Avogadro. It is based on the number of carbon atoms in 12 grams of carbon-12. Before we go any further about the atomic mass unit, you need to be familiar with the parts of atoms that are used. Electron, which has a negative charge, proton that has a positive charge, and neutron that has no charge. Let's use helium as an example. Helium has 2 protons and 2 neutrons, giving it an atomic mass of 4. The atomic mass is used to find the average mass of elements and molecules. Carbon atom has an atomic mass of exactly 12. 1 atomic mass unit is 1/12 of a carbon-12 atom. Not all atomic masses have whole numbers, but that's a different story. We can use this to figure out the mass of a particular atom. Pretty cool, right? It's mind-blowing.
Well done, Mr. Kiabu. You have received an A for this paper. And a matter of fact, because of your hair, I'll give you an A++. And that will average, your final semester score will average to a B. So, good job studying.
Thank you, Mr. Uwe.
Okay.
Listen.